This was called vestibulocochlear nerve. Yeah, not the mechanism up here. Not the mechanism up here. Vestibulocochlear PNS version. I think it's at the bottom of the list. As we said Thursday, Tuesday, one of those days. Vestibulocochlear nerve or system is actually two separate systems. Right? There's a vestibular system that deals with body position, head position, balance, and then the cochlear part, which is here. Functionally, this is classified as special somatic apharynx. And what other one was classified special somatic apharynx? Yeah, heard it in the back. Yeah, visual object. Okay. We are going to divide the ear into three parts. There's the outer ear, which consists of your pinna. This is also known as the auricle, flappy thing hanging off the side. There's an opening. This is called the external auditory meatus, or at least the opening to the external auditory meatus. And then you've got your tympanic membrane. The tympanic membrane will be the border between outer ear and middle ear. Tympanic membrane is the border between outer ear and middle ear. Within the middle ear, you've got three bones. Okay, up against tympanic membrane is the malleus, and then the bone in the middle is the incus, and then the last bone is the stapes. Okay, then we have our inner ear. The inner ear has our cochlea. That's what we'll be talking about today. It also has your vestibule and your semicircular canals, which we talked about Tuesday.
Could you repeat the names of the bones, please?
Yeah, we'll get that. Okay. So again, this picture diagrams the different regions. Outer ear, pinna or auricle. The opening is the external auditory meatus. The ridge, the rim of the ear, is called the helix. You have smaller ones, which are called an antihelix. They're labeled on the picture. I don't have it on my list. Tragus, it's a bump right in front of the external auditory meatus. It helps keep things out. Then you've got smaller bumps called antitragus. When we were an embryo, the tragus and antitragus were grown together to block everything. But as we developed, they separated out. The tragus is still there. It's really to protect things from going in. It doesn't stop everything. Tympanic membrane. That was going to be our order. Middle ear, that's where our bones are. Okay, up against the tympanic membrane, you've got the malleus. Okay, the tympanic membrane is also known as the eardrum. The eardrum drums with malleus. Okay, malleus. Malleus is also like a hammer. Our next bone is called the incus. that is translated into anvil. So if you're a blacksmith, you forge metal by beating on it with your mallet on an anvil. The last bone is called the stapes. It looks like a stirrup. Back in the Old West days, blacksmiths used to make stirrups by beating on metal with a mallet on the anvil. I don't know if that's true. It just fits my story. Yeah, it just fits my story. It makes sense to me. I think they did that. I'm saying the term that mallet, mallet is like a hammer. The tympanic membrane is the eardrum. So the malleus is attached to the eardrum. Now, if you can recall, all the way back to Tuesday, when we talked about the vestibule, we said there were two holes. What were the two holes?
The internal acoustic meatus and the external acoustic meatus? Or am I thinking of the wrong?
No. Good guess, though. We called them windows. So what were our two windows? Okay, well, what was one? What's the other? It's round. Okay, so two windows, oval window, round window. Okay, the stapes is going to be embedded in that oval window. Okay, so what these bones end up doing is a couple things. They're going to change the sound wave into something physical. On the other side of our on the other side of our oval window, we've got fluid. That fluid is going to be perilymph. Okay, so it's going to change the sound wave into a fluid wave. Also, because it's going from big space to small, it's compressing all that. By compressing it, you actually increase the amplitude. We went through these Tuesday. I keep thinking, I've said this before, you guys are just so fun, you make it seem like Friday. That's why I'm going to tell everybody so I can keep you around a little longer.
It's good to be appreciated.
On the bones, these bones, you've got a sound wave coming in that pushes up against the tympanic membrane, and these bones are going to then, your last bone is a stapes. They're going to move in a method that the stapes moves in and out like a piston, and on the other side you've got perilymph, and so it's pushing up against that perilymph, and so it's creating a wave of fluid. Fluid wave. Okay. Now, we've got our cochlea, takes 2.5 turns. Looks like a snail shell. Cinnamon roll. Okay, and inside you've got a membrane, which also takes 2.5 turns. The membrane was called the cochlear duct. Cochlear duct. Now, if we take a knife, well, we have to use a saw because this is bone, and cut through the cochlea, we'll get something that looks like this. All these little chambers. Now, I drew a box, so you're going to magnify the area in the box. In blue is your cochlear duct. There's fluid inside the cochlear duct. That fluid is going to be endolymph. Endolymph. Okay. On top, you've got a chamber called the scala vestibuli. On the bottom, you've got another chamber called scala tympani. Both the scala vestibuli and scala tympani contain perilymph. Perilymph. Okay, the cochlear duct was the blue in the middle. The blue in the middle is also known as the scala media. Our cochlear duct. Okay, so this is how this is going to work. I need somebody over there to shout. Okay. All right, sound wave comes in. Pushes up against tympanic membrane. Okay. The malleus is attached to the tympanic membrane, so as this membrane vibrates, the malleus moves. The incus is attached to the malleus. So if the malleus moves, the incus moves. Stapes is attached to the incus. So if the incus moves, the stapes move. This ends up being like a piston, going in and out, in and out, in and out. Okay, what is it going in and out of? The oval window. Okay. The oval window opens into the scala vestibuli. Scala vestibuli. Okay, this contains perilymph. So the sound wave, because of the stapes pushing it in and out against the perilymph, that creates your fluid wave. And depending on the frequency of that wave, that determines how far it travels. Okay. Lower frequency sound travels farther than higher frequency sound. Most sounds are actually complex, so you get sort of multiple movement.
I have a question about, I know people with depression, they have like a high-pitched noise all the time. Does this have anything to do with that? Like it's a high-pitched, like, breathing.
I don't know about
Yeah,
that.
it's nice.
Yeah, I don't know about that. Can't answer that, I'm sorry. Okay, so the lower the frequency, the farther it goes. Scala vestibuli, and actually they have this a little bit mislabeled. It should only go to about the tip here. So where you see the lines. Scala vestibuli. it's going to be connected to the scala tympani. The area where they connect is called the helicotrema. Okay, helicotrema. That's where the scala tympani and the scala vestibuli join. Helicotrema is where the scala vestibuli and scala tympani meet. So we have a continuous, I guess, I don't want to say flow, but sort of a flow. Continuous perilymph in those two areas. Right? Inside you've got endolymph. Now what we see here are fluid waves going to push up against the cochlear duct, create a little it is pushing in, and we'll see this on another picture. Eventually, it pushes in on the opposite side. We've got all this pressure built up in here that we have to relieve. And we do that through the round window. There's a little membrane here. It pushes out. It's almost like a valve. It pushes out into space. Your auditory tube would be right here, or your eustachian tube. That's that little bit of pressure out into the environment. And again, you know, it's case like a spit valve or some other pressure valve you might think of. On this picture, it shows low frequency travels further than high frequency. Most sounds are complex. Okay. Here's a magnified view of our scala media, which we also call what? Yeah, cochlear duct. The head fluid, endolymph. On top is our scala vestibuli, perilymph. On the bottom is our scala tympani, also has perilymph. Okay. So, because of our stapes pushing in and out of the oval window, which is located on the scala vestibuli, it creates a wave. Right? That perilymph wave. That's going to push up against Reisner's membrane. I still call it Reisner's membrane, but again, anatomists are trying to get away from using people's names and names of objects, so this is also known as the vestibular membrane. So, our fluid wave pushes up, the perilymph wave pushes up against Reisner's membrane, which creates a wave in the cochlear duct, in the endolymph. So now we have an endolymph wave. Okay, now from here we have a couple different ideas as to what might be happening. If you recall, Tuesday, we talked about receptors and, you know, macula and cristae. What were they made of? Do you remember? Yeah. Columnar cells. What were those columnar cells called? Hair cells. Hair cells. And they were called hair cells because of the stereocilia. And there was typically one stereocilia a little bit longer than the rest, which was called kinocilia. Yeah. And typically, on top of the stereocilia, there was what? Yeah, there was a membrane that had crystals on it, or there was a gel that had crystals in it. But there was something that the hairs could get stuck in. We have that. It's called the tectorial membrane. Okay, what's at the base of the hair cells? Nerve fibers, right. Okay, so we have this fluid going on here. One theory is that it pushes up against the tectorial membrane, and as the tectorial membrane moves, it causes the hairs of the hair cells. Now, there are others that say, no, tectorial membrane is too stiff to move. It's not going to move. What actually moves is this basilar membrane, which is much more flexible and thinner. And so it moves, the hair cells move, because the hairs of the hair cells are stuck in that tectorial membrane, they move. Right, again, the opposite direction. Whichever way it actually happens, the end result is that the hairs, if they move toward the longest hair, will release a transmitter, probably glutamate, which will stimulate the free nerve endings at the base. This area is known as the organ of Corti. Organ of Corti, or spiral organ. The neurons are bipolar neurons located in a ganglion called the spiral ganglion. So far. Okay, what happens to the perilymph and the scala tympani? There'll be a little wave going on there, which creates pressure. We have to relieve the pressure. How does that pressure get relieved? Round window. Okay, this is a picture of our tectorial membrane on our hair cells. Here's the organization of the hair cells. You've got 3 rows of outer hair cells, 1 row of inner hair cells. One other thing I want to point out, and it's a little technicality. There are some authors who say this longest hair isn't a true kinocilium. Okay, it's the longest hair, that's all I care about. I don't care what you call it. Call it Bob. You know, as long as the hairs go to the longest hair cell, it opens up the channels, it excites the hair cell.
So which one are the outer and which one are the inner?
If you go back to this picture, here's your outer. They're a bit bigger. Then here's your inner. Yeah. It's still called stereo. The little hairs on top.
So I can get a green side, so it helps which one it helps you look.
Right. Right. Okay. On top, we've got 2, these are called scanning electron micrographs. And you know, you might not want to call this a kinocilia, but it's different than all the rest. On this picture, you can see that the stereocilia are connected to each other through a little bridge. On the bottom left, okay, the top was scanning electron microscopy. On the bottom left, we have what's called transmission electron microscopy. And this is more like when you look at a slide. Microscope. This is more like looking at the outer surface. I actually always like using the scanning type because what it does is it puts gold on the top. That's what you're looking at, and it creates a nice little purple hue. Now our transmission version, you can still see the little bridge connecting our two stereocilia. The diagram is based off of the photomicrograph. And you can see as they move toward the tallest hair, this connection is going to open up channels and activate the cell. And we've seen this picture before. No, we haven't. Saw a version of this picture before. At rest, there is some activity. If you go toward the tallest hair, that increases. If you go in the opposite direction, that decreases. Okay, here's our outer hair cells versus our inner hair cells. Bipolar neurons within the spiral ganglion, which is embedded in bone. Here's a fluorescent microscope, micrograph of our hair cells. I put this on because it looked cool.
You took that yourself?
I didn't take this myself. I stole it. Actually, it's in the human brain by Monty. Okay, so here's our cochlea, our vestibular system. So here, yeah, the vestibular nerve. Here's our cochlea, cochlear nerve. They come together to form the vestibular cochlear nerve, internal acoustic meatus. That's getting you in the skull. Enters the brainstem lateral side with the pons meets the medulla.
So its origin is spawns.
I would say pontomedullary junction. Pontomedullary junction. So it's where the pons and the medulla join.
That's where it originates.
Well, it depends what you mean by originate. I mean, I would say it originates in the spiral ganglion.
But it just goes through the pontomedullary junction.
And it enters the brainstem at the pontomedullary junction.
So where would you classify exits?
It exits the cranium through the internal, well, I guess it exits the pectus part of the temporal bone through the internal acoustic meatus. Okay, my starting point is out here where the receptors are. So the fibers are coming in this way. And into brainstem.
It's because it's special sensory. And this is after.
Right, because these are afferents and the sensory. Yeah. Okay, this is the stained section. Way out on the side are your cochlear nuclei. Okay, and this is beginning in the medulla. So to get you an idea. Okay, so fibers coming in, watch my cursor, they're coming in, they're going to this cochlear nuclei. You have two, there's going to be a dorsal and a ventral, although both of them are really on the dorsal side. Okay, now, the simplest route, we've got a bunch of lines here, the simplest route. Fibers come in, they synapse in the cochlear nucleus. Our secondary nuclei cross over. The area of crossover is called the trapezoid body. It gets called the trapezoid body because all those fibers when you came in look like little trapezoid.
It's actually just about that.
They ascend up. The bundle that ascends up is called lateral lemniscus. And they will end at the inferior colliculus. This is a little nucleus in the big brain. Okay, synapse there. So these are going to be our third neurons. They then go to the thalamus. Okay, this bundle of fibers is called the brachium of the inferior colliculus. They go to the thalamus. The nucleus in the thalamus that they go to is called the medial geniculate nucleus. Okay, visual system went to the lateral geniculate nucleus. Auditory, medial geniculate nucleus. The visual system went to the lateral geniculate nucleus. Auditory goes to medial geniculate nucleus. Those are both nuclei of the thalamus. So the synapse there. I think we're at our fourth neuron now. Fibers come out. These are called auditory radiations. And they will go to the auditory cortex. Auditory cortex is going to be in the temporal lobe. Now remember early on when the sound wave was coming in, when I said lower frequency sound went further? Okay, that separation remains all the way through the pathway to the cortex. Okay, those frequencies are still separated out by the part of the cortex that they go to. Okay, the lower frequency sounds will be outer part, the higher frequency, deeper. All right? Then it's associational areas that sort of put it together make sound. Okay, so that was the simplest route. That was pretty simple. No? Agreement? No?
It was fun.
All right, but as you can see from the picture, not that simple. We've got some rest stops along the way. Do you know what the rest stops do?
Restaurants?
In the brain.
Transmission.
Every time you add a synapse, it increases time. All right? And if we just go through the basic pathway, each stimulus is an individual event. Okay? So if we don't fill in the gaps between those individual events, everything we hear would sound like it's vibrating, vibrato.
It's like prediction. Our brain predicts.
Yeah. So, if you recall that video we did during the visual system with the Blue Man Group, they talked about persistence of vision. Where the little spaces between the individual events sneak by. They're not really sneaking by. What you end up doing is having these, I mean, it's sort of the same process here. They're not really sneaking by, but because you've got these little rest stops, it increases a little bit of time between the gaps. So you have your basic one going at a certain rate, and then you have a little slower version of that going right behind it, filling the gaps. Okay, so that's what all these little rest stops are for. The other thing we see is fibers are crossing over and crossing back over every step of the way. Fibers are crossing over and back over every step of the way. Now, a lot of the fibers that are crossing back over are going to be inhibitory feedbacks. And we had inhibitory feedback with a lot of our sensory systems because you don't want to waste brain power. Well, actually, not with this. This is going to help you identify where the sound is coming from. The crossing over. All this crossing back and forth, back and forth. Okay, that's to help direct you toward where the sound is coming from. It sort of decreases one side, exaggerates the other side, so you can find where that sound is coming from. What's not up here, this even gets more complicated. What's not up here is everything going up also comes back down. There are reciprocal pathways. Now, what those reciprocal pathways will do is what I sort of started out saying before. Those are going to be inhibitory feedback loops so that sounds that are unimportant to you don't waste your brain power. I mean, if you just try to listen to all the sound going on right now.
So, I guess, in the case of like mesothenia, it's like this, what's kind of having problems with, like when people can't ignore certain sounds.
Yeah.
Does it have to do with the medulla? Like random loud noises to catch your attention or make you slow?
That would be midbrain. I can hear whispering, fans, cracking lights, people typing on their computer, people scratching with their iPad pen. Those points. Right? So there's all kinds of extra noise going on around you. You don't want to pay attention to all that. You don't want to pay attention to all that.
How did that relate to misophonia?
Misophonia is like when you get like physical agitation from like certain sounds, like chewing, like repetitive clock ticking, head clicks, like certain things like that. But I asked, I was like, is this the system that kind of is failing when that's like happening? Like when you cannot ignore the sounds.
And that's misophonia?
The descending reciprocal pathways. No, that would be a problem in the reciprocal feedback loops.
Is that curable?
I don't know.
Earplugs help.
Okay. When I was an undergrad, I lived in an area called Plaza. I was in Kansas City. Okay, Kansas City Plaza would be a little bit like that. know, with a roommate, it cost us $100 a month. Well, and then when we moved out, they paid us to move out. So we actually ended up making money. But we were on the ground floor. Plaza, again, think about head. Plaza is where they had the nightlife, clubs, the dining, you know, the restaurants. And we had a big parking lot next to us. And so people would walk up and down our street, you know, from the parking lot to the plaza. And it was Main Street. They misspelled the name, but you know, won't hold it against them. And we were ground floor up against the street. So there's a bus stop there. We always heard the bus, the wheel of tires, people walking up and down. I mean, would hear people going, "Thank God for the ground. If I weren't throwing up on it, I'd kiss it." Traffic all night, just sounds of the city. You know, first few nights, there was no sleeping. You know, after a while, because we learned those sounds weren't important, we didn't notice them much. One morning, gotta finish my story, but one morning we woke up and there was a car in our window. We didn't hear it. My roommate actually slept. We had no furniture. So he was actually sleeping right by that window. If that car would have gone much further, it would have been a big problem. Fortunately, it was slow enough. I think what happened was somebody hit the car that was parked and it just rolled it and tore it down. But we had gotten to the point where those sounds weren't important enough for us to notice anymore, although that would have been something we would have wanted to notice. But we had turned off all those type of city sounds. Right? And again, that's that reciprocal pathway that would be coming back down. True story. So that's it. I was hoping we'd have more time. You know, part of my plan today was to just do that last knowledge check together as a group.
But we still have 10 minutes.
So, I do not. It is time for us to leave. It is 10:50.